Can folks in the chat hear me? Thanks. Okay, so as always, remember the seating survey, Chem 112, Section 02, ILC 118. So as I mentioned on Piazza, for last week's homework, if you want an extension on it until Wednesday of this week, tomorrow, let me know. I'm happy to provide any extensions on that one. The material originally scheduled for this week is getting pushed off until next week. We don't know yet exactly how that's going to affect everything for the rest of the semester. I'm probably just going to be dropping some optional topics later on. So there are no content videos up right now, and the homework that is currently listed as due on Friday will not be due on Friday. I don't want to actually move it until I've figured out where everything's going afterwards, so that I'm not moving it twice. So don't worry, that is going to get moved. Thursday at 5, the plan is for exam number 2 to be released, and it will be due Sunday at 5. On the exam, there is what we know so far, post on Piazza. Essentially, there are going to be 3 parts to the exam. The first part is going to be analyzing kinetic data to figure out a rate law. And you're going to be doing that in a manner similar to what the practice spreadsheet that I put up on Blackboard does. There is a video on the YouTube channel that is a tutorial on how to use it. If any of you are using Macintosh computers, the keystroke sequences are slightly different compared to my tutorial. And there is a thread on Piazza that goes through what the differences are for that. The second part of the exam is going to be on the mechanisms and activation energy, transition state theory kind of portions of kinetics. And 2 Thursdays back, we went through an exam style question in class talking about that. So that's where I would go to find examples of that. And the third part is on equilibrium. You need to know ice tables pretty well. And I have a note that I added in Piazza that basically distills down what the information is that you need to know for equilibria and how to think about things like ice tables from the perspective of why they make sense to work the way that they do. Yes? They can't see my... There we go. Okay. Sorry about that. Thanks for pointing that out. All right. So that's what we know on the exams. There was a single muddiest point that was brought up on Piazza. Somebody saying that they were following through with the Excel spreadsheet on the kinetics practice spreadsheet along with my tutorial video and was getting different numbers than what I was getting. There are a couple of reasons for that, and I just want to make sure everybody understands what's going on with that. I made the video before I corrected an error in the spreadsheet on how the rate constant is calculated using the Arrhenius equation. I had a parentheses in the wrong place in the Arrhenius equation, and so when I converted the temperature from Celsius to Kelvin, I wasn't multiplying the whole thing by the, when I added 273 degrees to the temperature, that wasn't getting multiplied by R, the constant, the gas constant in the denominator. So I fixed that, but I didn't go through and redo the video as a result of that. So it is absolutely expected that you would be getting different numbers using the corrected spreadsheet. Secondly, even if we were doing it exactly the same, your numbers will end up being very slightly different because random noise is getting added to the data. And so when you are doing the analysis, the data points are going to be scattered very slightly from the positions that somebody else will have. And so down several decimal points places down, you will get a slightly different answer. You'll also find that different methods that you use will have different levels of accuracy. So for example, the method of initial rates is very sensitive to how short a distance you use in the data at the early times in order to consider that to be a linear region of the decay. And so if you take slightly different lengths of time, you will get different slopes for the initial rates. And as a result, that can make your answers differ somewhat from somebody else who's doing almost the same thing. So those are the kinds of things that need to be kept in mind. Okay, so that is essentially everything that I had on Muddiest Points, and so I would love to know what the folks in the chat and the folks that are here live would like for us to talk about in more detail. So we have those three main areas for the exam. We have the kinetic spreadsheet kind of stuff. We have the kinetic mechanism analysis, and we have the most recent topic of equilibrium using ice tables and such. What do people want to talk about most? Yes? Another kinetics mechanism. Sure, we can absolutely do kinetics mechanisms. So what I'm going to do, the problem with kinetics mechanisms is that I don't have memorized what some kinetics mechanisms actually are. So I'm going to have to use, A, B, and C and such for the various species. But yes, I can absolutely make up some mechanisms for us to look at and figure out how to analyze them. So let's see. Oh, there's a question here in the chat. Are we turning in the Excel spreadsheet as part of the test? No. So there will be questions in Blackboard about what is the rate law that you determine from the spreadsheet. And so things like what order in reactant A, what order in reactant B, and so on. That will be the information you'll be turning in, not the spreadsheet itself. Okay. So let's come up with a mechanism. We will say A plus B is going to be in equilibrium. We'll call this K1. We'll call this one K minus 1. Equilibrium with C. So C is kind of a dimer, a combination of the A and the B. We'll say that C can then react with another molecule of B to make, shall we do this one as an equilibrium? No, let's not do this one as an equilibrium. Let's do this as K2. And so this is then going to make D. D will then have a K3 process where it becomes our product E plus A. So in this mechanism, our overall reaction, and this would be some good practice for you to do, is to go through and look at what reactants you have, what products you have, and then what the overall reaction would be. So in this case, we would have A plus 2B plus C plus D goes to A plus C plus D plus E, and the A's cancel out, the C's cancel out, and the D's cancel out. So our overall reaction is 2B goes to E. And so what kind of species then is A for this reaction? A catalyst, that's exactly right. And what kind of species are C and D? Those are intermediates, right. Okay, so let's now see what we can do with this. The first thing to do, I think, is to write down the rate expressions for each step. So if we look at the rate for the forward reaction, the step here, what would we write down for that step as its rate? K1 times concentration of what? Of B? C. No, the forward reaction, so you use the reactants. So it would be concentration of A times concentration of B. Okay? What is R minus 1, the rate for the backwards reaction? So that would be K minus 1 times concentration of C. Right? What is the K2 rate, so R2? Yep, so K2, concentration C, concentration B. And then the last step, R3, what are we going to call that? K3, concentration D, right. Okay, so this kind of process of writing down the rates for the elementary steps, you should practice until this is second nature. You should be able to write one of these down in less than 5 seconds. Just, it needs to be that easy. And that skill of doing that will help you do exactly the same kind of thing when you're writing down an equilibrium constant expression, because it's the same idea. It's just the reactants and the products, and you just do products over reactants to make the equilibrium constant. Okay. All right, so now figuring out what the overall rate law would be for this, we have to make some kinds of assumptions, or we have to be told some information about it. So one of the things we might be told is to treat the intermediates as steady state. Okay, so we have C and D as intermediates. So we would want to have, one reasonable thing I could say would be, let's treat C and D as intermediates, as steady state intermediates. So what is the assumption we make for a steady state approximation? Concentration doesn't change. And we usually divide the steps into 2 categories. So there's the creation of the intermediate and the destruction of the intermediate. And so the approximation we would make is that the rate of production equals the rate of destruction. So if we look at the steady state approximation for C, we have the rate of production is governed by this step, the K1 step. So we have K1, concentration of A, concentration of B. We have 2 separate destruction steps. We have the reverse of the first reaction, and we have the forward second reaction. So what we do here then is say that we have the rate of production equals the rate of destruction, which is going to be K minus 1 concentration of C plus K2 concentration of C concentration of B. Okay, so if you have 2 things happening, then the overall rate is the sum of the 2 things that are happening. Okay. So what we are trying to do with this is to use the steady state approximation. So we are looking at the concentration of C being a steady state. So I'm going to label it with the SS subscript to keep myself straight about which species I'm interested in here. I'm now going to solve for that concentration. So on the right-hand side, let's factor out our concentration of C steady state. We get K minus 1 plus K2 concentration of B. Okay. Let's now, I need to close parentheses. We'll divide through by the K minus 1 plus K concentration of B. So we get our C steady state equals K1 concentration of A concentration of B over K minus 1 plus K2 concentration of B. Okay, everybody with me at that point? What I did was I divided both sides through by this thing in parentheses. Okay. Okay. We also need to have our, we need to deal with our I can't talk, let's try again. We need to look at our D concentration as a steady state. So we have the rate of formation of D, which is going to be K2, concentration of C, concentration of B, is going to equal the rate of destruction of D, which is going to be K3 times concentration of D. Now that's our steady state. So our concentration of D steady state is going to be K2 over K3, concentration of C, concentration of B. Well, but concentration of C steady state, we already have up here. So let's plug this into this so that we can get a concentration of D steady state that doesn't have any intermediates on the right-hand side. So we've got K2 over K3 times our concentration of B times this thing up here. So K1, concentration of A, concentration of B, over K minus 1 plus K2 concentration of B. Okay, so we can try to simplify that into, let's see, K1, K2 over K3 times concentration of A, concentration of B squared times 1 over K minus 1 plus K2 concentration of B. It's probably even better to have that underneath here, but you probably get the idea from the math. Now, we need to figure out what's our overall rate. So this is just our D steady state concentration. Well, the product in this reaction is E, right? So the rate of formation of product would be our overall rate. So our overall rate is going to be K3 concentration of D, which we have here. So plugging that in, our K3s are going to cancel. So it'll be K1, K2, concentration A, concentration B squared over K minus 1 plus K2 concentration of B. And so we now have our overall rate law that this mechanism predicts. Whenever you see a case like this where you have two terms in the denominator, you have a situation where there isn't a straightforward reaction order. This isn't just a rate constant times concentrations to various powers. But usually you can identify two different regimes for this to be operating under. Either this is big compared to this, in which case we neglect this one, or this is big compared to this, in which case we ignore this one. Okay? So in those two cases, the first case where K minus 1 is big and we can ignore K2b, our case A, then we have K1, K2 over K minus 1, concentration A, concentration B squared. Okay. In case B, where the second term is the dominant one in the denominator, case B, we have K1, our K2s cancel, and be concentration A, concentration B. So we have two different cases here. In the first case, it's second order in B and third order overall. In the second case, it's first order in B, second order overall. And so let's think about what that means in terms of the steps. This is saying that for the first case where K minus 1 is dominant, that says that this reaction going back from C is faster than this reaction here. Okay? The second case, where K2B is the dominant factor, is saying that this step is fast compared to the reverse reaction here. And so let's suppose that we experimentally made the measurement and found that our reaction rate was second order in concentration of B. We could test this mechanism. We would make a prediction from this that if we bump up the concentration of B to very, very high values, that would make this term start to dominate. And so we would then predict that at really high concentrations of B, the rate law would change to becoming first order in B. That general idea, reasoning process make some sense? Okay. So the goal for the way I would handle this in the exam, I don't have this part of it written just yet, so I can't be incredibly specific about it right now. But the way I want to handle it on the exam would be to give you two different mechanisms. So this would be one mechanism, and I would say use the steady state approximation here. Then I'd give you a different mechanism where I would say, okay, in this one use the pre-equilibrium approximation. Something like that, in a different mechanism. And then you go through it and see, do I get the same rate law or do I get different rate laws? And then you would talk about, first off, what rate laws do you get? And then secondly, how would you experimentally tell which of those two mechanisms works better? Which of those is more likely to be correct? Does that general idea make some sense? Okay. All right, anything else on kinetic mechanisms before moving on to another topic? It looks like there are requests from the chat on ice tables and Le Chatelier's principle. So, but if there are more questions on mechanisms, let's deal with that before we go ahead. So in the chat, in pre-equilibrium, K1 equals K minus 1. Yes, so pre-equilibrium assumes that the equilibria are fast compared to other processes. And so you make the forward rate equal the reverse rate. That is what the pre-equilibrium approximation states. And so the way that would work here would probably be saying, use the pre-equilibrium approximation here and assume that the second step is rate determining, is what you would have to do. Okay. Okay, with nothing else on mechanisms, ice problems that would be similar to an exam question. So I do not have the equilibrium questions written yet. So I don't actually know. So the first thing that I would say is I would probably give you an equilibrium that has several components that both on reactant and product side, and also has stoichiometric coefficients that aren't just one, so that you have to figure in those components. So coming up with one of those off the top of my head is difficult, but let's suppose we have something like A aqueous plus 2B aqueous plus C solid is in equilibrium with 3D aqueous plus 2H2O. Okay, so something like that. So the first thing you would do is write down the expression for the equilibrium constant. So KEQ, what will that be in this case? A little louder, whoever's talking. Correct. So the one thing I'm going to do to refine this, just as a reminder, is write an EQ subscript by each of these to remind us that this relationship holds only once you have reached equilibrium. Okay, so if you don't have the EQs in here, then strictly speaking, what we would have here is a reaction quotient rather than the equilibrium constant. So the next thing we would have to do would be to write our ice table. So I unfortunately went onto multiple lines here, so it wasn't going to work. So I will do A plus 2B in equilibrium with C. Nope, I'm not even doing that right. Let's try again. A plus 2B plus C in equilibrium with 3D plus 2H2O. And we notice that the C, because it's a solid, does not participate in the equilibrium expression, so you can get rid of that column. And the water, because it is the solvent, similarly does not participate, so we can get rid of that column. Okay. So in order to do any ice table problem with this, what we would do is we would either be given an equilibrium constant and some initial conditions, or we would be given enough information to find the final equilibrium concentrations, and then would calculate the equilibrium constant from that. So there are two different ways you could go. So for example, let's say that we have an equilibrium constant here that is 5.3 times 10 to the 8th. Okay. And let's say that we start with 0.1 molar of A, 0.3 molar of B, and we start with 0D. Okay. What do you think the first step would be for us? Identify the change. There is one step I would recommend doing before we get to that point. Okay. The first thing to do is to step back and say, how likely is it that we are starting close to equilibrium? Looking at our equilibrium constant, it's huge. It's very big. What does that mean about whether this reaction that we've written is product favored or reactant favored? Product favored, because products are in the numerator, and so you need a large numerator in order to have a large equilibrium constant. So the very first thing I would do is to create a shifted initial state where we assume, let's move the reaction as far to the right as possible, and then our starting point will be closer to actual equilibrium. Does that make sense? So now, if we imagine running the reaction as far to the right as possible, which of A or B is our limiting reagent? A, because we have 3 times as much B as A, and we only use up twice as much B as A. So we're going to have the 0.1 of A all react away, giving us 0. If 0.1 of A reacts away, 0.2 of B reacted away, leaving us with 0.1 left. Okay. If 0.1 of A reacted away, 3 times that much of D appears, so this becomes 0.3. Everybody follow that step. Okay. Now we look at this and say, are we close to equilibrium? Probably. It's not going to be exact because we're not going to have 0A, because that would mean we would have 0 in the denominator, and so that's not going to end up equaling a number. But it's probably going to be small, whatever is here. So we are probably close to equilibrium. So we now have to say, what is our change? So if we're starting here and we have a change, can we go below 0? No. So that means this is going to be our x, positive value. This has to go up by something. If this goes up by x, what happens to B? Goes up by 2x. If this goes up by x, what happens to D? Goes down by 3x, right. So what you have now in this situation, just from the stoichiometry, is how much it shifts as it goes to equilibrium. Our E line's the one we don't even have to think about, we just add it down. X, 0.1 plus 2x, 0.3 minus 3x. Okay. Now, we could take this and plug it in directly, but notice what's going to happen if we do that. Our B is going to be, we're going to have x squareds there, right? And our D, we're going to have x cubes there. And so that starts to get a little nasty. We can do it, and particularly if we plug it into something like Wolfram Alpha to say, hey, solve this polynomial for me. That's fine, you can do it that way if you want. But since we already made the observation that we are probably pretty close to equilibrium, let's see if we can make some simplifying approximations to make the math work easily. So I'm going to switch colors and pens here so that we can identify that we are doing an approximation. So we're going to assume that this 2x is small compared to 0.1, and that this 3x is small compared to 0.3. If we do that, then we look at our equilibrium expression. Is everything fitting? Almost. Okay, and so we say now our KEQ, which is 5.3 times 10 to the 8th, is going to equal D cubed, so that's 0.3 cubed, over A, which is an x, and B squared, 0.1 squared. Okay, so x is going to be 0.3 cubed over 5.3 times 10 to the 8th times 0.1 squared. So I'm going to put that into a calculator. So 0.3 cubed divided by 5.3 times 10 to the 8th divided by, open parentheses, 0.1 squared, close parentheses, equals, x equals 5.1 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the negative 9 molar. So 5.1 nanomolar is what we end up getting. And now at this point, we go back and check. Was the approximation we made that 2x is small compared to 0.1 valid? Absolutely. Same thing for 3x compared to 0.3. So this kind of ice problem factors in pretty much all of the skills and knowledge that, that you would need to have to be able to do basic equilibrium problems. And so this is the kind of thing that I would imagine throwing your way for as an exam question. Yes?
I just want to refresher as to why you didn't include the plus 2x and the minus 3x.
Sure. So the idea there is that we can include it if we wish to. And it's just that if we do so, then we're going to be squaring something with an x, and we're going to be cubing something with an x, and we'll end up with an unwieldy polynomial that's difficult to work with. And so what we are doing then is saying, can we simplify the math so that we don't have to deal with that annoying polynomial by neglecting the changes? And so what we did was we said, in this box here, we have 0.1 plus 2x, but we think we are starting very close to equilibrium because we already shifted things over towards the product side. And so because we think we're starting out very close to equilibrium, that means that the shift that we have based on the x's is going to be very small. Okay?
So then if there wasn't that close to equilibrium, or at least the beginning of that equilibrium shift, then you would include the plus 2x as well.
Absolutely correct, yes. If we didn't have a good reason to believe that we were already close to equilibrium, then we would have to include the plus 2x and the minus 3x. If our equilibrium constant here were 12, we would not call that product favored. I mean, it's a little tiny bit product favored, but not enough that we would say it's all going to be product. Yes.
Could you solve the ice table without shifting it?
Could you solve the ice table without shifting it? Kinda. The problem is when you do that, let's look at that. So if we do it without shifting it, then I'm only going to draw the 3 columns. So we're starting at 0.1, 0.3, and 0. We would say, and so this is where the equilibrium's happening here. So we're saying we're going from here to here. So this would have to be 3x, this would be minus 2x, and this would be x, right? So 0.1 plus x, minus x, 0.3 minus 2x, and then 3x. Our problem here, when we go through this, is that x is going to be large at this point. In fact, it's going to be almost exactly 0.1. And so when we go through the math, we can't neglect the x and the 2x here. So we're going to have a higher order polynomial we have to solve. And when we do so, the result that we get is going to be x is going to equal 0.99 or 0.99999 1, 2, 3, 4, 5, 6, 7, 8, 4, 4, 9, something down in that neighborhood. Okay, just based on what I saw the x was over in this case, it's going to be something like this. And the question at this point is, do we really trust this many significant digits on this number? I certainly wouldn't. So we know that it's going to be close to 0.1, but are we going to be able to trust the number we get here in this box for how much A is there at equilibrium? No, can't trust it. So doing that initial shift solves both of those problems. It lets us start closer to the eventual equilibrium, and that allows us to make the math easier, and it means that we can trust the results because we're not running up against sig figs. Yes?
And then this one, you change it to 0.1. Is there a reason it's 0.1?
When we initially shifted from the top line to the second line here, why did we shift by 0.1? Because by shifting by 0.1, we completely run out of A. It goes to 0. And so that's as far as we can go. Does that make sense? Okay. All right. Okay, let's see. Do we always want to try to get initial values closest to equilibrium right off the bat? It helps. It helps with the math because it helps us be able to neglect the small changes. And so yes, looking at the equilibrium constant and seeing, can we get close to equilibrium early, it helps us helps us pretty well. Can we still find the answer without doing the second part of one? Okay, so I already went through that. Yes, and that one would not be fun to solve. Okay, so it looks like we're caught up on the chat comments. Any last questions on this ice table example? Right, so the second question that was, second topic that was brought up in the chat is Le Chatelier getting confused on words like compresses, expands, contracts for volume, pressure, container, and how they all interact. I think I have it in the next one, get the next one wrong. Okay, absolutely. So the general idea for Le Chatelier is we have an equilibrium, and whatever perturbation we apply, the reaction shifts in the direction to reduce the effect of that perturbation. So if we add extra on the product side, then the equilibrium shifts away from that. If we take away extra on the product side, then some of that missing products gets filled in by shifting from the reactant to the product side. That's the general principle of Le Chatelier. We can look at that by simply expressing Q relative to K. So remember that Q is equal to K at equilibrium. Also remember that both of these are products over reactants. Okay, so if we add extra product, then that means that we end up with a larger Q, and so our products is then going to be greater than K if we add extra products, right? So how does this ratio get back to K? It gets back to K by numerator turning into denominator, which means products turning into reactants, which means reaction shifts left. Okay? So that's the general way to think about Le Chatelier. Now let's apply this to the idea of gases, because that seems to be the point of confusion for what was specifically brought up. So the general idea is that you compare the reactants to the products to see which side has more moles of gas. Okay. So let's suppose that on the reactant side we have 3 moles of gas, and on the product side we have 2 moles of gas. Okay, so 3A in equilibrium with 2B, something like that. Okay, so if we do something now to increase the pressure, so we then are compressing the gas, for example, which increases the pressure of every component, then Le Chatelier says that the reaction shifts in a way to relieve some of that pressure. So if the 3 moles of gas on the left turn into 2 moles of gas on the right, then you've got less gas, and so overall the pressure goes down. Okay. The way to see that in terms of the reaction quotients like we were talking about before is that if we start at equilibrium with Q equals K, and then we do something like double the pressure. So we half the volume, which doubles the pressure. Remember, PV equals nRT. And if we leave this side constant, we're not changing N and we're not changing T, then if we half the volume, we are doubling the pressure in order for that to stay the constant equal to the right side. So if we do that, then we have, I'm doing 3A in equilibrium with 2B. Then what we have is pressure of B squared over pressure of A cubed for our equilibrium constant. If we are doubling the pressure, then what's happening is that our new Q, so let's do Q new, is going to be our initial pressure of B initial times 2, that whole thing squared. Right? We've doubled the initial pressure, and this is then going to be over double the initial pressure of A. There should be another I in there. And that's cubed. Now let's factor that out. So our Q new is now going to be 2 squared or 4 over 2 cubed or 8 times the pressure of B initial squared over pressure of A initial cubed. But this right here is our equilibrium constant because we said we started at equilibrium. So this is now saying that our Q new is 1/2 our equilibrium constant. So our Q is too small. In order for our Q to become larger again so that it goes back up to K, you have to turn denominator into numerator. Turning denominator into numerator means that you are changing reactants into products and our equilibrium is shifting to the right. So the idea here is that when you're trying to understand Le Chatelier's principle, there are multiple ways to think about the problem, but if you're doing it right, they all should give you the same direction. Looking at it in terms of, I'm increasing the pressure somehow, so the reaction needs to shift in the direction to relieve some of that pressure, gets you directly to now the reaction is going to shift towards the side that has fewer moles of gas. If you are more comfortable thinking about it in terms of reaction quotients, that shows you why that's the case. Okay, so the initial inquiry about this is saying getting confused on words like compress, expands, contracts for volume with the pressure in the container. So the idea here is that it all comes back to PV equals nRT. So if you expand your volume, then that means you're making the volume larger. And because of that, the pressure will go down. If you compress it or contract the volume, you're making the volume smaller, and so the pressure will go up. Okay. Yes?
So I was wondering if it's the same amount of moles on each side of and reactants, would there be no change?
That's exactly correct. So if there are the same number of moles of gas on the left and the right-hand side, then changing the volume, changing the pressure will not shift the equilibrium. Absolutely correct. There is a third way to think about how this reaction, how Le Chatelier shifts in response to what we're dealing with. So the third way to think about it is in terms of kinetics. Remember that equilibrium is very specifically meaning that the forward reaction rate equals the reverse reaction rate. Well, if you take this mixture that has reactants and products in it, and you compress it, the effect on the number of collisions on the left-hand side is going to be greater than the effect on the number of collisions on the right-hand side, because you need 3 things colliding here, whereas you need 2 things colliding here. So that means that when you compress the gas, when you change the volume, then the forward reaction is going to become faster relative to the reverse reaction, and so that means the equilibrium is going to shift towards the right. So that's 3 different ways to look at Le Chatelier, and they all give you the same answer. Any further clarifications on Le Chatelier as it applies to gases, or even expanding it to Le Chatelier as it applies to anything? No? Okay. All right, what else can we talk about? I've been a little surprised at how few questions have been coming in about the kinetics spreadsheet. Is that because the tutorial was sufficient to get you through it, or is that because people haven't been looking at it yet? I'm guessing the latter of those. And yes?
I'll be real, I just haven't gotten to it yet, but then
Okay.
again, I was also seeing that there was homework on Friday, even though I knew that technically that wasn't a thing because of the email, so I was just generally confused, so I started working more on the homework.
Gotcha. Yeah, so one of the reasons why I pushed everything off, other than me getting sick, which was a part of it as well, but I also wanted to make sure you guys had plenty of time to get comfortable with the kinds of Excel analyses that are going to be needed on the exam, and that's through practicing with that spreadsheet. If you are not incredibly adept at Excel already, then it's going to take a little practice to get down pat what the methods are, what the methods are to select the regions you want so that you can copy a formula all the way down, or that you can bring data from one place to another, or that you can make a plot of the X and the Y that you want to make the plots of. So, so practicing those skills is going to be something that will help you a great deal and save you time on the exam, because you'll have those skills down. Okay, so there's a question here. I'm still really confused on how we will be using the spreadsheet after watching the video. Okay, so this spreadsheet is a practice version of the spreadsheet. This spreadsheet is one where you can go in to the second tab and set up pretty much any rate law that you want, that as long as it's of the form rate coefficient times concentrations to 2 powers, and then generate data using it, and then go analyze that data. The version on the exam will be a different version I give you, where you will only have access to, it's going to be protected, you'll only have access to the first sheet. So I will have set up a kinetic model that will be similar to the kinds of things that you can set up in the practice sheet, but you won't have access to it. The only access you will have to it is by running experiments, getting the data from the experiments, taking them over to your own spreadsheet and analyzing the data so that you can figure out what the rate law is. Okay, yes?
So the spreadsheet that you're using is also powered through Excel?
Yes,
Okay.
yes. So, so what I am doing for the exam version of the spreadsheet is I'm taking the version I gave you and I'm updating it with a specific kind of kinetic model, and then protecting it so that you only have access to the front page. And then the questions on the exam will be, okay, starting from this concentration set of concentrations, run an experiment. Is the resulting kinetics that you get 0th, 1st, 2nd order, something like that? Then I'm going to say, using that starting point, use so that you know that this will actually run the experiment and you can get data from it. Construct for yourself a new set of concentrations you're going to take data at in order to use the method of initial rates to figure out the rate law. Once you do that, tell me what order the reaction is in species A, species B, species C, and so on, and what is the rate coefficient. Then, now that you have a way to do this, run a temperature series so that you can tell me the activation energy. So something like that is what you would be doing. So does that, Haley asked a question in the chat about this, does that help in understanding what you're going to be doing with the spreadsheet? Yes.
So I watched the video and you did it in like 3 different parts, kind of. Are
Uh-huh.
you going to do that 3 of those parts for one problem, or are you going to do 3 of those parts for like multiple problems?
So there will be, what I took you through was how to first determine if a given set of data is simple first, 0th, 1st, or 2nd order. If you're doing the method of flooding, which was the last example I went through in the video, you have to do that first part too. So I may or may not actually ask you a specific one like that first one. If you're doing the method of initial rates, that's going to be, that's sort of a different kind of thing because you're only looking at the very, very early times. And so that one is kind of distinct from the others, though it gives you another way to get at the same information that method of flooding does. At the moment, I am still trying to pick which kinetic system I'm going to have you guys doing. I wanted it to be a real system rather than these arbitrary A, B's, and C's so that it actually felt like you're solving an actual problem. The problem I've been coming up against is that the examples I've been finding I haven't been able to get activation energies for every single one of the steps that's involved in it, and so I can't get the overall activation energy very well. So I'm still trying to figure out which one I'm going to be doing. So at this point, I anticipate that I would give you direction about you should use method of flooding or you should use method of initial rates. I don't think just based on time that I'll ask you to do both of them, because both of those give you the same information in the end. And each of them is also relatively time consuming. So I would probably only have you do one of those two. So in a Piazza thread, there's one Piazza thread where somebody had asked me, being concerned about the amount of time it takes to do things in Excel. And I understand that. And so I timed myself using the skills that I talked about in Excel in that video. Running one experiment, taking the data over to a new spreadsheet, and determining which reaction order it is and what the rate coefficient is took me about 1.5 minutes. Okay, so my suggestion in that thread was set yourself up a simple first order decay and practice the skills of getting the data into into your own Excel spreadsheet and figuring out what the rate coefficient is, knowing its first order, until you can do that in about 3 minutes. Okay, about double what it took me to do. Then try the same thing for it being second order rather than first order, and see can I still do it in 3 minutes. You know, then I timed myself as well. Once I knew what my time was on the first one, I said, how long is it going to take me to do an entire method of initial rates? And it took me 7.5 minutes. And so my suggestion was, you guys should see if you can set yourself up a method of initial rates problem with like a first order in A, second order in B, and maybe half order in a catalyst or something like that that you have. And then see, can you get down to about 15 minutes to figure out that that's what the reaction order is. So, it's, once you see the procedure, it's relatively straightforward. You just have to sort of get the muscle memory for when do I shift click, when do I control click in order to get the sections of the data selected you want in order to plot and being able to efficiently do that. So that's kind of the limiting factor in using Excel in this case. And so I talk through it, how to do that in the video. And if questions come up about, boy, I keep not getting the control click right when I need to, I can talk through with you how that works. So question here, does the tutorial show us how to, quote, run an experiment? Yeah, yes it does. So basically all it is you enter in the concentration, the initial concentrations you're going to have, and the data just shows up. As soon as you hit enter after putting the concentrations in, the data is there, and so you just copy and paste the data out. That's all it is. You don't even have to press a button to say run experiment. It just generates the data. Okay. All right, we have about 5 minutes left if there's anything else anybody wants to chat about. If not, then okay, we can be off a little early. Thank you all.